Uh, I, I'm going to prove this for you, mostly because the proof is easy. In other words, I'm going to prove that that's true. And as I give the proof, you'll see where the convolution is coming from. That's number one. And number two, the real reason I'm giving you the proof, because it's a marvelous exercise in changing the variables in a double integral. Now, that's something you all know how to do, even the ones who are taking 1802 concurrently, and I didn't advise you to do that. But I've arranged the course so it's possible to do. But I knew that by the time we got to this, you would already know how to change variables in a double integral. So, and in fact, you'll have the advantage of remembering how to do it because you just had it a week or two ago, whereas all the other guys, it's something dim in their distance. And so I'm reviewing how to change variables in a double integral. I'm showing you it's good for something. So what we're out to try to prove is this formula. Let's put that down so you understand. Okay, let's do it. Now, we'll use the desert island method. So you have as much time as you want. You're a desert island. In fact, I'm going to even go it the opposite way. I'm going to start with, you got a lot of time on your hands, say, gee, I wonder if there's if I take the product of the Laplace transforms, I wonder if there's some crazy function I could put in there which would make things work. You've never heard of the convolution. You're going to discover it all by yourself. Okay, so how do you begin? So we'll start with the left-hand side. We're looking for some nice way of calculating that as the Laplace transform of a single function. So the way to begin is by writing out the definitions. We couldn't use anything else since we don't have anything else to use. Now, looking ahead, I'm going to not use t. I'm going to use two neutral variables when I calculate. After all, the t is just a dummy variable anyway. You'll see in a minute the wisdom of doing this. So it's this times the integral, which gives the Laplace transform of g. So that's e to the negative sv, let's say, times g of v dv. Okay, everybody can get that far. And now we have to start looking. Well, this is a single integral, an 1801 integral involving u, and this is an 1801 integral involving v. But when you take the product of two integrals like that, remember, when you evaluate a double integral, there's an easy case where you don't, it's much easier than any other case. If you could write the inside, if you're integrating over a rectangle, for example, and you can write the integral as a product of a function just of u and a product of a function just as v, then the integral is very easy to evaluate. You can forget all the rules. You just take all the u part out, all the v part out, and integrate them separately, a to b, c to d. That's the easy case of evaluating a double integral. It's what everybody tries to do, even when it's not appropriate. Now, here it is appropriate, except I'm going to use it backwards. This is the result of having done that. If this is the result of having done it, what was the step just before it? Well, I must have been trying to evaluate a double integral as u runs from 0 to infinity and v runs from 0 to infinity of what? Well, of the product of these two functions. Now, what is that? E to the minus su times e to the minus sv. Well, I must surely want to combine those. E to the minus su times e to the minus sv. And what's left? Well, what's gets dragged along. Du dv. This is the same as that because of that law I just gave you. This is the product of a function just of u and a function just of v. And therefore, it's OK to separate the two integrals out that way. Because I'm integrating over sort of a rectangle. It goes to infinity that way and infinity that way. But what I'm integrating is over the plane, in other words, this region of the plane. As u, v goes from 0 to infinity, 0 to infinity. let's take a look. What are we looking for? Well, we're looking for, we would be very happy if u plus v were t. Let's make it t. In other words, I'm introducing a new variable, t, u plus v, and it's suggested by the form in which I'm looking for the answer. Now, of course, you then have to, we need another variable. We could keep either u or v. Oh, let's keep u. That means v, this game of musical chairs, v got dropped out. Well, we can't have 3 variables. We only have room for 2. But we will remember it. Rest in peace, v was equal to t minus u in case we ever need him again. Okay, let's now put in the limits. Let's put in the integral, the rest of the change of variable. So it's e. So I'm now changing it to these new variables, t and u. So it's e to the negative st. Well, f of u I don't have to do anything to. But g of v, I'm not allowed to keep v. So v has to be changed to t minus u. Amazing things are happening. Du. Now I want to change this to an integral du dt. Now for that you have to be a little careful. We have 2 things to do to figure out this, what goes with that, and we have to put in the limits also. Now those are the 2 non-trivial operations when you change integrals change variables in a double integral. So let's be really careful. Let's do the easier of the 2 first. I want to change from du dv to du dt. And now to do that, you have to put in the Jacobian matrix, the Jacobian determinant. Aha! How many of you forgot that? I won't even bother asking. Oh, come on, you only lose 2 points. It doesn't matter if you put in the Jacobian. As you see, you know, if you're going to forget something, you'll lose less credit for forgetting that than anything else. So it's the Jacobian of u and v with respect to u and t. So to calculate that, you write u equals u, v equals t minus u. And then the Jacobian is, blah, 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 blah. The matrix of, the determinant of partial derivatives. So it's the determinant whose entries are the partial of u with respect to u, the partial of u with respect to t, but these are independent variables, so that's 0. The partial of v with respect to u is -1. The partial of v with respect to t is 1. So the Jacobian is 1. So if you forgot it, no harm. So the Jacobian is 1. Now, more serious, and in some ways, I think for most of you, the most difficult part of the operation is putting in the new limits. Now, for that, you look at the region over which you're integrating. I think I better do that carefully. I need a bigger picture. That's really what I'm trying to say. So here is the uv coordinates, and I want to change these to ut coordinates. The integration is over the first quadrant. So what you do is, when you do the integral, the first step is u is varying and t is held fixed. So in the first integration, u varies, t is held fixed. Now what does holding t fixed in this picture mean? Well, t is equal to u plus v, so u plus v is fixed. Is a constant, in other words. Now, where are the curves along which u plus v is a constant? Well, they are these lines. These are the lines along which u plus v equals a constant, or t is a constant. The reason I'm holding t a constant is because the first integration only allows u to change. T is held fixed. Okay, you let u increase. As u increase and t is held fixed, I'm traversing these lines in this direction. That's the direction on which u is increasing. I integrate from the point, from the u value where they leave the region, enter the region. What's the u value where they enter the region? U is equal to 0. Everybody would know that. Not so many people would be able to figure out what to put for where it leaves the region. What's u, the value of u, when it leaves the region? Well, this is the curve v equals 0, but v equals 0 is, in another language, u equals t. T minus u equals 0, or u equals t. In other words, they enter the region where u equals 0, and they leave where u is t, has the value t. And how about the other guys? For which t's do I want to do this? Well, I want to do it for all these t values. Well, now the t value here, that's the starting one. Here, t is 0, and here t is not 0. And if I go out and cover the whole first quadrant, I'll be letting t increase to infinity. The sum of u and v I will be letting increase to infinity. So it's 0 to infinity. So all this is an exercise in taking this double integral in uv coordinates and changing it to this double integral, an equivalent double integral over the same region, but now in ut coordinates. And now that's the answer. Somewhere here is the answer, because look, if I, since the first integration is with respect to u, this guy can migrate outside because it doesn't involve u. That only involves t, and t is only caught by the second integration. So I can put this outside, and what do I end up with? The integral from 0 to infinity of e to the negative st times, what's left? A funny expression, but you're on your desert island and found it. This funny expression, integral from 0 to t, f of u, g of t minus u, du. In short, the convolution, exactly the convolution. So all you have to do is get the idea that there might be a formula, sit down, change variables, the double integral, and echo, you got your formula.